Okay, hey there guys, and welcome to this video where we're going to speak about the Haber process. Right, so you need to know that the Haber process is the process by which we produce ammonia using hydrogen and nitrogen. You also need to know the reaction conditions in the industrial process, right? More importantly though, you need to know why those reaction conditions are chosen and that it is a compromise based on yield versus rate. And we're going to have a look at the reasoning for all of that in this video. So let's have a look right now. Okay, so first let's take a look at the chemical reaction of the Haber process, right? It looks something like this. You've got nitrogen plus 3 hydrogens makes 2 ammonias. Notice that all 3 of them are gas. By the way, nitrogen and hydrogen we need to obtain. Nitrogen we obtain from the air, and hydrogen we get from natural gas, right? From natural gas and steam. Okay, I just wanted to mention that right from the get-go. So, by the way, if you have not seen my video on reversible reactions and you're not comfortable with equilibrium, then please go and have a look at that now, because this topic really relies on you already knowing that stuff back to front, right? Okay, so this reaction actually is a reversible reaction, okay? Which means that there is going to be an equilibrium and the conditions affect that equilibrium, right? First, we're going to have a talk about temperature. So, what you need to know is that the forward reaction, okay, the forward reaction is exothermic, and so therefore the backward reaction is endothermic. And so that means that operating this reaction under different temperatures is going to give you different results. And so the important things to realize are that we are going to be affecting the yield and we are going to be affecting the rate, okay? Both of those things are extremely important, particularly in industry. If a reaction happens but you're not producing anything at any kind of speed, then it's completely pointless, right? And also, if a reaction is happening and you're not producing any of the product, then it's pointless, right? And so that's an extreme example, but you get what I mean. So if we operate this reaction at low temperatures, okay, based on Le Chatelier's principle, that is going to favor the exothermic direction, and we're going to get a higher yield of ammonia. And remember, ammonia is what we want. Okay, so if we use a low temperature, then we are going to get a high yield. Okay, which sounds all well and good, but a low temperature also gives us a low rate. Okay, and just one thing is that if increasing the temperature actually increases the rate drastically. Okay, if you don't remember, please have a look at my video on collision theory and how temperature affects rates of reaction. Okay, now the temperature affects the rate of reaction more drastically than anything else, right? More drastically than things like surface area or concentration or pressure, which is important here. The temperature is actually really important for that. And so having a low temperature really reduces and limits the rate of a reaction. Okay, so that's not good. Having a high temperature, okay, is therefore the opposite. A higher temperature actually favors the endothermic direction, meaning the equilibrium lies more to the left, and we don't get as high a product. We don't get as high yield, so we get a low yield, right? We obviously wouldn't get as much ammonia, we'd get more nitrogen and hydrogen. However, a high temperature gives us a high rate, okay? And remember, as you increase the temperature, the rate would increase drastically, right? Not just linearly. Okay, right, so that's temperature. Pressure also affects what we are going to get. And so, if we take a look, notice that on the left-hand side, we have 4 molecules of gas, right? 1 nitrogen and 3 hydrogens, that's 4 molecules of gas. And on the right-hand side, we have only 2 molecules of gas, right? 2 ammonia molecules, and that's it. That means that technically the pressure of the left-hand side is higher than the pressure of the right-hand side. And so the equilibrium moves in order to counteract that change depending on what we do. So if we operated this at a low pressure, the equilibrium is going to move to increase the pressure, okay? And so it's going to move to the left. Okay, so that means we'd actually get a lower yield, right? A lower yield, because the equilibrium would shift this way to the left. Okay, and by the way, pressure, of course, also affects rate, and a low pressure also means a low rate. Okay, so both those things make low pressure sound like a no-no. Okay, now one thing to mention is that pressure, in comparison to temperature, doesn't affect the rate as much, right? Temperature has a more drastic effect on rate than pressure does. Okay, so if we increase the pressure, we are actually going to get a higher yield, right? A high yield. Because remember, the equilibrium, if we increase the pressure, is going to move to reduce it, and so it's going to move this way, okay? And also, we are going to get a higher rate at a higher pressure. Okay, a higher rate at a higher pressure. And so that makes us think, well, having a high pressure is obviously the way to go. Let's make the pressure as high as possible in this reaction. Okay, one thing, which I'm going to write here in silver to make it seem like it's money, is that a high pressure is very expensive, right? So a high pressure is expensive. Okay. If you want to make a chemical reaction occur at a very high pressure, you need very specific apparatus to do that, right? You need apparatus that can actually withstand massive high pressure. That's really expensive, right? Normal lab equipment cannot withstand really, really high pressure. Okay, so it costs a lot of money. It also costs a lot of money to generate that high pressure. And so that's two things. One more thing is that it's dangerous, right? If you use crazy high pressures, you've got a constant danger of explosion. And so that is going to be the reason why, as you'll see, we actually compromise. So, in summary, if we use a high temperature, then we are going to get a lower yield, right? Not a higher yield, we're going to get a lower yield. However, the reaction is going to be much faster, right? A high temperature also costs money to produce, not in the same way that pressure does, right? So what about a high pressure? A high pressure will give us a higher yield, it will give us a faster rate, but not to the same extent as the temperature, and it's going to be a much higher cost to do that. And so what we actually do is we compromise all of these things, right? We think, well, we want a high temperature in order to get a fast rate, okay? However, it's going to cost us money, and also it's going to mean we're going to actually produce less product than what we want, right? And so we have to compromise or meet somewhere in the middle there. And then what about high pressure? Well, a high pressure will give us a higher yield and a faster rate. And so both those are great. We want to do that, but they pose dangers and they cost a hell of a lot of money. And so we don't want to go all the way, right? We can't actually afford to do that. It would not be economic. And so we actually reach a compromise, and that compromise is this: 450 degrees Celsius. Right, 450 degrees Celsius. It's a high temperature, but it's not in the thousands. If it was in the thousands, we'd get a really fast rate, but we'd have a much lower yield. Okay, 200 atmospheres of pressure. Now that is a high pressure. It is a high pressure, but it's not 1,000 atmosphere pressure, which would pose serious problems in terms of cost. Okay, finally, we use a catalyst. It turns out that iron can be used as a catalyst, right? And remember, a catalyst increases the rate of reaction without being used up, and so it costs a bit of money in order to buy the catalyst, but then it can be reused, and so that is a no-brainer. So these are your overall conditions, and that is the reason you can be asked to talk about the compromise that you have made between yield and rate. The point is, you want a fast rate because a really slow rate messes you up. You can't produce product in time. However, you also want a high yield because a high yield just means you get more of the product for the amount of reactant that you use, right? One thing I would mention as well is that in this reaction, when, for example, nitrogen and hydrogen are reformed because you don't get a massive yield, what we do is we recycle them and just use them again. You put them back into your reaction chamber and you use them again, and so that serves to increase the yield, and so that is great. Okay, so that's enough of me talking. I hope that made a lot of sense. That compromise between rate and yield is extremely important, and you need to understand reversible reactions in order to get that. So we will stop there. Please feel free to comment in the box below if you still have any questions, but I hope that did make sense. Also, please like and subscribe as usual because that really does help me out. But I hope you enjoyed the video, and I look forward to seeing you in the next one.